Thanks for bearing with everyone. Great to be with everyone here today. Great community, and thanks for taking this cold, wintry Wednesday night to be here with us. The title is a little bit, dramatic, as titles are wont to be, because we're not going to train something to beat GPT-4 at everything, but specifically we can beat GPT-4 at the thing that you want to do with large language models or generative AI. And we are going to do that by mobilizing first-party data for the purposes of fine-tuning. So this is a very, very classic machine learning data set. It's called Fashion MNIST, and it's just grayscale articles of clothing. And the job of the neural net or your machine learning algorithm is to figure out what this item is. GPT-4o, if you ask it what the item is and you do it over a bunch of examples, we'll get about an 81% accuracy over this task. It's multimodal, it works out of the box with vision, so a lot of people are like, great, GPT-4o works with vision, that means we don't need any vision models anymore for the rest of our lives. If you take a simple tree-based model, like XGBoost and train it to predict what the item is, you get about like 90% accuracy, which is A, significantly higher when you think about the fact that it's getting it wrong half as often. Two, it's not even a complicated thing. This is a CPU-bound training that is done widely over tabular data, and we're kind of applying. Oh, we didn't do a sound check, so well. It's a loose contact. Yeah, I can try with this. And maybe this is better. And if you use like the standard 10-year-old model that you would use to target this task for predicting the outcome of the image, it's about 95%. And so you can think for any like enterprise use case, for any like mission critical or even important use case, using something out of the box is pretty good and gets you most of the way there with zero effort. But putting some effort in and doing something that is, approximately 9-10 years old will get you, 75% better outcomes. And this is a point because in 2025, writing code is actually extremely easy. So you should be trying to maximize your quality and outcomes instead of using GPT-4o out of the box. It's really good at writing code, so why don't we have it write some code instead of doing the thing that it's not super good at, which is identifying whether it's a skirt or a pair of pants. And so machine learning has always been about winning with data. And to be controversial or cynical for a minute, AI labs have a vested interest in telling you that you shouldn't train your own models. If you go back 10, 20 years and you think about how Facebook and Meta have built their businesses, it was about the fact that they mobilized their first-party data way better than every other ad agency, right? Like Don Draper went on Mad Men, but he didn't mobilize his first-party data, and now Google is a $2 trillion company, and Don Draper is not, right? So, and imagine if Facebook just did all their advertising through like the Google Display Network, right? They never mobilized it; they just put Google ads on their site. Or imagine if you don't mobilize your first-party data the way that every big player in tech is mobilizing first-party data. Well, these people are spending billions to train new models, so there's clearly value. And by the way, like this is just another piece of shade in a shady slide. None of them are using SageMaker to train models, right? Like it's kind of a black box, and you kind of have limited options. So this is to say that a lot of people want to keep you comfortable and not thinking about how to advance your model quality and want you to be focused on kind of just using things out of the box. That being said, like there's a difference, I think, between application engineering with large language models and generative AI and these tools, and like cynically being like you don't need to mobilize your first-party model data. And I think one of the things that before we kind of jump into fine-tuning is velocity is competitive velocity, right? Even for bread and butter language model use cases, the winners are optimizing, right? If you're doing unstructured data extraction, a lot of that is based on transformers architecture that is extremely popular now. and is the basis for GPT. These methods are being used broadly outside of text generation, and the architecture is extremely broadly useful. But basically, the companies that are experimenting the most quickly are going to win, and the companies who are using off-the-shelf things are always going to be slightly behind that first group. So, apologies for review for people who maybe are more familiar with some of these, but just to quickly define a few terms, back of envelope, there's more nuances, obviously, than what can fit on one slide in a few minutes. But one, pre-training is what is being done by AI labs across the world, right? Meta does pre-training to create Llama 3, and they train on massive diverse data sets, coding, all the books. When people go on Twitter and go like, we've already trained on the sum total of human knowledge, that's because almost every AI lab across like Anthropic, Meta, et cetera, are basically already doing pre-training across all of the sum of human information, right? And so that's kind of, if you follow Twitter take havers, pre-training is kind of a commodity at this point, and basically all the AI labs can do it equally well, and it's not something that like really you need to do here. This is done at a scale of thousands of GPU clusters run for a long time. They burn nation states of energy, but by and large, it's irrelevant for most of us. Fine-tuning is refining that pre-trained model for specific tasks, contexts, domains. This is instruction following. If you've ever gone and looked at the open source meta models, you'll notice that they'll release the pre-trained model, and then they'll also release one that's -instruct. That means that model has already gone through a lot of work in order to be fine-tuned to follow your instructions, so that when you say, hey, write me a poem to do this, it doesn't just go on a tear and just keep generating tokens forever. Prompt engineering is adjusting the input to the language model. You have to remember that language models have been held out as this like weird new AI technology, but fundamentally like predicting whether this is a skirt or a pair of pants, or famously on Silicon Valley, there was the whole hot dog, not hot dog prediction. It's all the same thing. All language models are doing is predicting the next word one token at a time. And so by prompt engineering, you're changing the input data in the same way that if you change the picture, you would get a different prediction. Prompt engineering is about changing the input data to get different output tokens, right? If you put more context, more text, then you can also start doing that dynamically. You can have retrieval augmented generation, which is extremely popular and very much of the moment, which is about finding and incorporating extra information into the prompt, frequently dynamically on the fly, based on semantic relevance rules to produce better answers. There's a lot of literature and tooling around making sure you find the right information. But fundamentally, these last two categories do not touch the model, right? When you see like Llama 405 billion parameters, the first one is changing 405 billion parameters. The second one is hopefully changing a lot less. And the last ones are putting different things into this box so that you get different things out of the box. This differentiation is important because, they're not to some extent overlapping, right? They're very orthogonal with each other, and that you can apply more than one of these things at the same time. I already kind of touched on this, but almost every model that you've ever seen has been actually fine-tuned, because by and large, unfine-tuned models are garbage and don't do anything. ChatGPT only was able to successfully commercialize GPT-3, which had been out in the wild and like labs for a long time, because they taught it how to respond to chat. And then you would have a conversation with it and you would be like, this is great. Before, you would ask it a question, it would just generate a giant wall of text, and you would say, this is not great, right? Llama 3.1 was pre-trained on 15 trillion tokens, which is, roughly, 12 trillion words. But then they only did about 25 million synthetically generated examples to do the fine tuning. So you can see that there's multiple orders of magnitude of scale difference between the pre-training and the fine tuning. But here is a critical point. GPT-4 needs to, you see these like benchmarks on like how they're all 80% at the LSAT, and like what, you don't need the model to pass the LSAT, right? It can write poetry, it can classify sentiment, it can write code, it can do all of these things. But if you work at a bank and you're like, oh, I want to like grade my customer service calls, I just wanted to classify sentiment. I don't need the poetry bits, right? And I think this is an important part that is like critical to understanding why fine tuning is valuable, right? You can make a giant model that is just so big and so good at everything that you can win all these awards and get hype. And you can also make a smaller fine-tuned model for a specific precise task that will not take the LSAT, but will do a really good job at classifying customer service sentiment. So the benefits are, one, domain-specific knowledge. The fine-tuning is over all things, but not necessarily your internal code base. It's not necessarily over your domain area. Maybe you would want it to be a medical expert, but you don't want to have to call out to GPT-4. You want to be able to have an internal, very private, very secure medical expert, and so you can train some generic model over domain-specific knowledge and have that be a model that you host. You can have extremely fast. Oh, this is kind of a nonsense sentence. It's extremely fast. You have lower latency time. You see a lot of people now talking about small language models, SLMs. People have used LLMs so much, it's like Kleenex, right? Like people forget that the L means large. But if you have large language models, that means you can also have small language models, right? You want to hit like a less than 100 millisecond latency, as opposed to when you send an API call out to OpenAI, it can take 15 seconds to get a turnaround. And also you're relying on like the throughput, right? And so with small language models, you can deploy a fleet of specific tasks, focused ones, and you can have those respond almost instantaneously. And that's pretty good if you're building an application that relies on the language model to make some kind of decision. Brand safety, hallucination reduction, improved precision. This is like, I think, a common claim for fine tuning. I think it happens. It's more on the evaluation side, I would say, right? Evaluations is like you generate a bunch of stuff and then you create some system to test and systematically understand if it's doing well. I would say that brand safety, hallucination reduction is much more on like how well you're building an evaluation stack, but fine tuning could create a more brand safe, more robust model for yourself. And then finally, you can unlock rapid at scale experimentation instead of relying on third-party updates, right? There's a large number of people whose products will get 30% better when GPT-5 comes out, but they will not improve their model quality until GPT-5 comes out. And so in these long intervals of like doing nothing, there's a lot of iteration time that is being lost and at-scale experimentation by only trusting pre-trained models rather than trying to go and target fine-tuning on your own. At large enterprises, you see these like banks and large organizations already doing a lot of custom code models that have been fine-tuned over their internal code bases. This works significantly better than out-of-the-box generation because you'll frequently have libraries that are internal libraries that there's just no way that there's going to be a generic code model that knows that. And techniques like RAG, like trying to pull in the context on the fly, have just incredibly long latency times where if you need to go and do that round trip, it's not going to be as snappy of an inference experience. And you can build RAG on top of a fine-tuned model, and there's ability to layer these things as well. AI agents is the only thing on my LinkedIn feed anymore, but AI agents is actually like a stacking of just traditional software engineering and building applications, with some of those decisions being made probabilistically through machine learning or AI. AI agents make these decisions, and to make those decisions really well, you don't necessarily need the poet laureate GPT-4 to make those decisions. In fact, it will not do that really well, right? Going back to that image classification example, I would rather fine-tune something to do this specific task and make the decision more often and be smaller and faster at doing it. So AI agents, if you go out and look at all these vertical SaaS companies, a lot of their secret sauce is some kind of fine-tuning over some set of models that are very domain specific. They package that up and then they deliver it to you as an application called an AI agent, but that's to some extent traditional software engineering. Not to say that they're not powerful, it's just to say that it's like, just rebranding software. And then finally, you can make transformers architecture suitable for traditional ML tasks. I hinted at this. Like, if you think about what, if you go all the way back, not quite 10 years, BERT, bidirectional encoder by Google, was invented because they wanted to return Google search results to you that were more semantically relevant. And so actually a lot of the origin of what we think of as like GPT-4 and like these text generation models were originally content understanding models as well. And you can take these powerful models and apply them in creative ways to things like content understanding again. I don't know if you remember, but like Google Translate was like really bad and now it's really good, right? And like some of these advancements are actually advancements in transformers architecture. And then just like objection handle, it's like, I heard this is expensive or difficult. And I think that's not true. And the reason for that is because I think people hear these numbers of how much resources are required to pre-train the models, but you can go and take a 7 billion parameter model on an A100 for $5 an hour, for $2 if you're using spot instances, and run it for like 4 hours, and that's it. It's like $20, right? Like I have the cash in my pocket to do that. You can train large models like the 70 billion parameter models on clusters of 2 to 4, and like no matter how much data you have in your organization, it's like really not that much, right? It's like probably a 24-hour task. Basically, for $1,000 you can fine train whatever model you want. So like there is a problem still, which is that data curation is incredibly hard, right? If you think about like what OpenAI did, they like hired thousands of people globally to like do all these like reinforcement learning, and data labeling is $1 billion business. Scale AI basically just labels data as a $1 billion company. So data curation is really difficult. But my guess is that your company has done a huge effort over the last 5 years to create a great data estate, right? Like all the investments into Snowflake, Databricks, et cetera, has been like a effort to govern data, make it traceable, give it lineage, auth, governance. And now it's sitting there waiting to be used. And so it's a relatively good time. But data curation is hard. And if you have a particular use case, one of the most difficult challenges will be making sure you have the clean data set to kind of operate off of. If you want to rate the sentiment of your conversations and you want to do it, make decisions as an application, you will need some set of examples like the agent making this decision in order for it to fine tune for that decision. 2, infrastructure setup is huge. Like this has been the problem that has plagued machine learning for like the past couple of years. Getting the code to run successfully on multiple nodes of GPUs is still like what I would classify as like a hard task, right? There's companies whose entire job is to abstract it away from you. But this is probably like the engineering piece that is somewhat difficult. In practice, like there's a little detour out to like a company pitch, right? Like I work at Runhouse, we do a little bit of ML infra. Basically, the problem that like the team set out to solve was that data scientists and machine learning engineers spend a lot of their time wrestling with infrastructure. When you think about like what differs from like data engineering or like what happened in the past with like smaller data sets, you could run it on your laptop. With traditional software engineering, if you're building a website, you can see what it looks like. When you go from local development to scaling to multiple GPUs on a remote instance with multi-node orchestration, that's a engineering task that requires platform effort. And like where we like to go with like our like stupid startup analogy is like, hey, Runhouse is like Snowflake for ML, right? Snowflake really did a great thing, which was that before Snowflake, if you remember, there was Hadoop clusters, right? And it would be a pain in the butt to manage them, and they were not super accessible, and you had to do infrastructure if you wanted to scale your SQL queries from something that would run on that single node to something that would run over a terabyte of data. After Snowflake and OLAP databases and many other things, anyone writes a SQL query, whether it's a query over 100 rows of data or a billion rows of data, and then they send it to Snowflake. They like write this malformed query and like put it in an Airflow node, and then they run it, right? And it magically distributes over ephemerally allocated compute, which is a great cost savings that Snowflake claims. And that's entirely opaque to you, and then you get the results back, and you didn't need to think about infrastructure, and you could go fire the people who manage the Hadoop cluster. This is better, except for those people. And so like what we really do is write before Runhouse, you would maybe write a toy program over local compute. Toy not because it was not serious code, toy because it was not operating on full-scale data. When scaling to production, you would start doing something called like ML ops, which is a terrible long effort by an engineer or specialized tooling. But with Runhouse, what you do is you just write regular Python programs that are generic to generic Python programs that are using undecorated regular code. We do some magic, and then we execute it over ephemerally allocated cloud compute that's launched from the pool of all available compute. And we think this is better. And there's governance, auth, et cetera. And so, but now I just kind of want to give a demo from a code perspective. as I said, because Runhouse works over regular undecorated code, we can actually talk a little bit about what the training loop or like what the process of launching a fine-tuning looks like. Before I get there, maybe I'll pause quickly for questions. Okay, so here I just have a model class. So I said that there are a lot of abstractions and libraries now that are available for you to use that to kind of make fine-tuning extremely easy. And so I think supervised fine-tuning trainer by Hugging Face is one of the most popular ones. And so if you have some data set and you just kind of load that base model, here we're using auto model for causal LM. You load the model by name, it pulls it, downloads it from Hugging Face and brings it into memory. Load a tokenizer, right? Tokenizers break up long chunks of text into tokens. I don't remember the specific name that Llama 3 uses, but you need a tokenizer in order to kind of take text and carve it up for use by the LLM. Now you've loaded the model, right? Fundamentally, you've kind of made just two function calls, one to load the model, one to load the tokenizer. We have some load data set, right? The data set is up to you, right? You bring in your data that is curated. These are examples of the task you want to fine tune for. And then there's this monster thing that it has a number of options. We will not exhaustively go through them, but you could have as few as 2 and as many as you want. And these are extensively documented online. And most of the time, you should just copy one that someone else wrote, and it will probably work, right? It governs how quickly your fine-tuning learns. And the parameters are important, but if you just run it for longer, they may not be that important. And then kind of all you do then is say, I have a model, I have a data set, I have some parameters and a tokenizer and some parameters again, and then this will just run, right? Like when you call tune, more parameters, there's just like a lot of parameters, like ultimately like through this 120 lines of code, which you mostly can rip off the internet, by the time you call trainer.train, you can see that this process will take you through and actually do the fine tuning. This example is publishable on GitHub, and so we can share it afterwards. But the main point of this demo wasn't to say like this is the syntax you should follow. The main point of this is like you call 2 functions to load the memory, and you define a bunch of configs, and then you just call train, and they will go. And then at the end of it, you will save it to disk, and that will be your fine-tuned model. In order to load it and run it, right, you can just define a function, generate. You load the tokenizer, you load the pipeline, you load the model, and you just kind of call the pipeline, and out comes the text. All of this has been magically abstracted for you by like the people who do like Hugging Face, open source development, right? And so within 150 lines of code, you've actually just been able to write a fine-tuning script. And if you cut out all the spaces, I bet you could fit it into 70 lines of code. And then I'll briefly mention that like Runhouse, right? Like how we work is you define a cluster, it pulls it out of AWS. You take that and you send it to you take your regular class and you send it to the cluster, and then you call .tune. And then if you run who is Randy Jackson, then out will come answer. I think we're running out of time, and so I'll pause here and then flip to, I guess, a conclusion slide. And if anyone has questions, or right now or later, shoot us an email, or I don't know what the Q&A process is for the meetup.